Hi, this is Math 1650 and this video is over section 6.3, and we are going to be looking at sampling distributions and what makes certain measure a better estimator and what makes it a poor estimator. Right, so a couple of things here. One, we're going to be sampling with replacements, right? And so these are going to be samples from large populations, or the idea is that they come from large populations in order to make them mainly independent events. Now we're doing sampling of samples. And so a sampling distribution is a probability distribution of sample means where all samples are the same size. Alright, so let's just think of the numbers 1, 2, and 5. Okay, let's just look at what an average of those three numbers would mean. Okay, so let's say the population is 1, 2, and 5. Now I know this isn't a large population, but it's small enough that we can actually get every possible sample, which is why we're going to do it. And we want the average. So the population mean is going to be 1 plus 2 plus 5 over 3, which will be 8 over 3, which is going to be 2.67 basically. Okay, so now let's look at each of these samples. 1 and 1, 1 and 2, 1 and 5, 2 and 1, 2 and 2, 2 and 5, and 5 and 1, 5 and 2, 5 and 5. And find the mean of each of these. So basically averaging each of these out too. So when they're the same, it's just 1, the same number. So 1 and 2, the average is 1.5. 1 and 5, the average is 3. 2 and 1 is 1.5. 2 and 2 is 2. 2 and 5 is 3.5. 5 and 1 is 3. 5 and 2 is 3.5. And 5 and 5 is 5. Now each of these values, samples, has a 1 in 9 chance of happening. Okay. But let's condense this into our sampling distribution. So the values we have are 1, 1.5, 2, 3, 3.5, and 5. Right. 1 happens once, so it's a 1 out of 9. 1.5 happens twice, so it's a 2 out of 9. 2 happens once. 3 happens twice. 3.5 happens twice. 5 happens once. And we add these up, it should equal 9. So 3, 4, 5, 6, 7, 8, 9. Okay. So complete distribution here. Now you remember with distribution, to find the mean, you take the value, you multiply it by that probability. So we'll multiply each of these together. So 1 times 1/9 is 1/9. 1.5 times 2/9 is 3/9. 2 times 1/9 is 2/9. 3 times 2/9 is 6/9. 3.5 times 2/9 is 7/9. And 5 times 1/9 is 5/9. And then we add all these up. So 4, 5, 6, 12, 19, 24 over 9. which breaks down to 8/3 or 2.67. Right, so the mean from the population was 2.67. The mean from our sampling distribution was also 2.67. And so this means the mean targets the population mean. So the more samplings you have, your mean is going to be closer to your actual population mean, even if you're not using all of the population. And especially if you're using a large population. Let's do the same thing with the median. Okay, 1, 2, and 5. Population median is 2. That's pretty easy to find, just the middle number. Now let's look at the median between these. If they're the same, you have to average them. So the median between 1 and 1 is 1. Median between 1 and 2 is 1.5. Median between 1 and 5 is 3. 2 and 1 is 1.5. 2 and 2 is 2. 2 and 5 is 3.5. 5 and 1 is 3. 5 and 2 is 3.5. And 5 and 5 is 5. And each of these has a 1 in 9 chance of happening. So this is your sampling distribution. So we're going to write this out in an ordered data set. So we're going to look at the sampling distribution. 1, 1.5, 1.5, 2, 3, and 3, 3.5 twice, and 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we take the middle number. So 4 on this side, 4 on this side, your middle number is 3. So your median from the sampling distribution is 3. You may think, wasn't supposed to probably be true. No, not in this case. Median is not a good estimator. It does not target the population median. So it doesn't matter what your population median is, or your sample median will not necessarily follow that. So just because you've done a sample and you get a certain median doesn't mean it is actually the actual median of the population. But we'll do another one. We will look at proportions. Okay, so we'll look at proportions of odds. So for our population, we have 1, 2, and 5, and the proportion of odds is equal to 2/3. That's from the population. So let's look at the proportion of odds for each of these. So 1 and 1 is 2/2. 1 and 2 is 1/2. 1 and 5 is 2/2. 2 and 1 is 1/2. 2 and 2 is 0/2. 2 and 5 is 1/2. 5 and 1 is 2/2. 5 and 2 is 1/2. 5 and 5 is 2/2. And each of these has a 1 in 9 chance of happening. And so if we look at this, we have 100%, 50%, and 0%. 0% happens once, so 1 out of 9. 50% happens 1, 2, 3, 4 out of 9. 100% happens 4 out of 9. Right, so if we multiply these, so 1 times 4/9 is 4/9. This is your proportion, sampling distribution. 1/2 times 4/9 is 2/9, and then 0 times 1/9 is 0. And when we add these up, we get 6/9, which breaks down to 2/3. Alright, so a proportion of odds from all samples is 2/3. The proportion targets the population proportion. Alright, so there are other good estimators and there's some other bad estimators. Right, so the good estimators, we've seen the mean, we've seen proportions. Another good estimator is variance. Okay, you may do that in your homework. And then the standard deviation does not target the population standard deviation, but the bias is small for large samples. And when we get to the central limit theorem, we'll realize that what we do is have a correction to the standard deviation to make it on target. Bad estimators, we saw the median, and then the range is only a bad estimator. I'm sure the mid-range is probably a bad estimator as well. Alright, so in 6.4 we're going to look at the central limit theorem. I'll see you then. Bye.